I am going to be talking about, actually when I came here, I got this booklet. It says, the future is here. And if I do my job correctly, I will tell you what's there for the future of future. Okay. So I think you can see the title there. I'm going to be talking about quantum technologies. And I will be going through, first, I'll first tell you a little bit about to sort of say what quantum technologies are. There are certain myths about quantum technologies. Many people think it's just quantum computing, but it's not so. It's beyond just computing. I'll also tell a little bit about how quantum technologies are going to catch up or are going to complement the AI, but cutting-edge technologies. AI is one of the main ones. I'm going to then talk about the roadmap that Karnataka, as well as India, and globally, where we are with this technology, and where do you think we will go in the next 5 years to 10? Okay. First, the myth. Quantum technologies is not just quantum computing. There are three aspects of quantum technologies. First, of course, is quantum computing. And quantum computing is a new paradigm of computing that uses quantum physics in its certain nuances. I am going to tell you a little bit because I am with a lot of people who probably haven't seen quantum physics for a very long time. So I'm going to tell you what rather weird aspects quantum technologies are built on. In addition to quantum computing, there's quantum communications, the way we communicate completely in a hack-proof way in the next few years. That's going to be quantum communications. And finally, the quantum sensing and metrology. The quantum technologies will build in a whole new class of sensors that's going to help us in medical diagnosis, help us in GPS-free navigation, and so on and so forth, which is where some of the advantages as well as some of the risks come in. Okay, just a little bit of what quantum is built on. What's the fundamentals of quantum? So we know that there's a classical computer that is there. You have all the beautiful laptops and very fast computers, the workstations. They are built on classical bits, which are essentially these transistors which are in 0 and 1 state. Quantum is built on slightly different stuff. If you think about these states as a vector, it's not up and down, but just two vectors, then quantum is essentially built on this kind of a situation where these two vectors can exist simultaneously. I'll give you an example for that. Assume that you look at the person next to you, then you look away. Now, if you look away, you don't know if the person is sitting next to you. So if I ask you, is the person next to you is sitting there or not, you will say, yeah, either yes or no. The quantum world says that's an incorrect answer. The quantum world says the person is there and not there. So this is what is called the concept of superposition. It's actually non-intuitive or counterintuitive or whatever you say, but that's what quantum theory is built on. So this is called superposition of two states, and when we measure, it collapses into two actual states, which means now you turn around and you actually see if the person is there or not there. So that's called a measurement. So this is what quantum theory is built on, and it says that the state can exist in all possible states between yes and no, which is what gives it the power. So now, instead of just 1 and 0, you can live in infinite number of states which are combinations of 1 and 0, which is why a quantum computer in certain tasks will be infinitely faster than a classical computer that you see today. Okay? So you can stay everywhere here, all right, or everywhere there. That's how quantum computer works. And now, of course, it cannot be done in the same transistor that our computers are built on. So there are other technologies. I'll not go in that. You use superconductor, semiconductor, various other platforms. You use it. Little bit of history, because we are just celebrating the 100 years of quantum technologies, which is why the UNESCO has declared this as the International Year of Quantum. For example, what is so interesting about quantum that it has been debated over the last 100 years? So suppose I have this qubit, which is the state of superposition of two up and down or yes or no. and I make two of them, and I, what you call, entangle them quantum mechanically. Don't worry about, you don't understand the word. Trust me, even I don't understand the word. So suppose we entangle them, and then we let it go very, very far away. Say one goes to Mars, other goes to Jupiter. And you have two persons, say, for example, Alice and Bob. So this qubit goes to Alice, and Alice measures it. And if it measures it continuously, she will get either up or down, yes or no. And it's going to be a statistical sequence of numbers. So if Bob measures it too, in Jupiter, say, very, very far away, the Bob will also get a statistical sequence of up and down. Problem is that if they're entangled, then these measurements are perfectly correlated. And that's tricky. It means as if I'm sitting in Mars and I'm making a measurement, it is instantly affecting the measurement that is being done in Jupiter. And this is what the whole concept of entanglement is. And this is why our man, Albert Einstein, way back in 1930s, didn't like it at all. So he and his friends came up with a theory called the hidden variable theory. And for the next 30 years, that was debated. It was in a state of flux. But then a person named John Bell in Bristol University said that, okay, we can check whether the quantum theory is right or the hidden variable theory of Einstein is right. And it turned out that the quantum theory was right, and for that, proving that, three gentlemen got the Nobel Prize in 2022. So that's a bit of history. We do not understand how this spooky action at a distance works, but over the last 100 years, we have found out a way to engineer it and make a new generation of computer, and that's what, let's go ahead and try to find out what happens. Right now, there are various ways a quantum computer can be built. There are technologies based on superconductors, semiconductor, trapped ions, photonic qubits, and so on and so forth. There are major companies in the world who are trying to make these quantum computers. What people want now is a roadmap of when a quantum computer will be available with us. For example, IBM says a useful quantum computer will be available around 2033. Google says, well, we will get it sooner. We'll get it roughly around 2029, 2030-ish, using superconducting qubits. Okay? These are superconducting companies which are making superconducting quantum computers. QEra is making trapped ion quantum computers. And then we have IonQ, which is going to say that in about next 5 years, you will have a useful quantum computer which will do certain tasks very, very weird and interesting way. Okay, how does a quantum computer look like? This is a circuit, a computer circuit, superconducting quantum circuit. And on this, there is this bit that I talked about. It's not really a bit of a transistor, but it's a bit made of superconductors. This is then put in a large cryostat, which goes down to minus 273 degrees centigrade. 273 degrees below the room temperature. And that's where this operates. And then there are all sorts of circuits which you do the measurement using RF pulses that goes like this. So this quantum computer will not look like the one which you have in front of you. It will look very, very different. It will occupy a much larger amount of space, and it is going to be far more expensive. In addition to that, we have quantum communication. Quantum communication is essentially how you communicate, how you send information. Usually, quantum communication depends on single photons. So if you look at the light there, we have about 100 trillion photons that come every second towards us. We need to deal with one of them. And this is what quantum communication is built on. I send you a single photon, you send back to me a single photon. And in that single photon, there are certain ways I encode information, which is usually polarizations and things like that. And if there are hackers which are sitting in the process, then you can detect that there is a hacking going on. And as a result, you can detect somebody is listening to what you're saying, somebody is taking the data away from you, and you can then stop it. So that's how the quantum communication works. So there are various ways. Eventually, the goal will be to have quantum internet, all cryptography, integrate quantum cryptography into communication system. This is the goal of quantum communication. Look at satellite communication with single. China has already moved enormously. They are already communicating with Austria and other countries to using satellite-based single photon generation and detection. In addition to that, in about next 5 to 10 years, we are looking at a quantum internet where all our information around the internet is going to be based on single photon-based encoding. Last but not the least, as I told you, is the quantum sensing and metrology. What can we do with quantum sensing and metrology? We can make a gravity sensing. We can measure the acceleration due to gravity with a 1 part in 1 billion using quantum sensors. Why is it interesting? Imagine two things. One is oil and gas exploration. When you go over the Earth crust, if you see slight change in the density of the Earth crust, you should be able to see if there is natural reserves underneath the Earth crust. So that's one. Second, inertial navigation without the GPS. When an aircraft flies, it takes the different altitudes. Gravity changes with altitude. So aircraft knows exactly where you are, exactly how high you are from the Earth's surface. Hence, navigation without GPS support is one of the major areas of gravity sensing. In addition to that, we can measure clocks, extremely high accuracy clocks. You know, financial transactions, the share market opens in New York and that in India, the financial transactions start at the same time. So we need to find high quality clocks in order to standardize time. So we require a whole class of different displacement sensing and gravity sensing equipments, atomic clocks, magnetic sensing, and quantum radars. For example, using magnetometers based on quantum sensors, tomorrow I should be able to measure tiniest of magnetic fields that can tell me the NMR, the magnetic resonances that we do in our NMR machines when we go for MRIs, for example. So we would like to replace large magnetic fields for biodiagnosis. So these are areas in which quantum technologies are going to come in. I'm now going to go into the economics aspect of it. So, which are the key stakeholders for quantum computing? We are talking about oil and gas. I gave you some examples of it. Sustainable energy. We are looking at typical economic impact in these areas. For example, looking at financial services. By financial services, I mean to say from timestamping in transactions, credit card fraud, looking at ATM machine tampering, for example. All these areas are going to be direct beneficiary of quantum computing and quantum sensing. And we are talking about an economic impact of nearly $2 trillion over the next 10 years or so. What is happening in the market today? And the quantum computers have already started, quantum computing companies have started generating revenues. For example, if you take a look at the projection in 2035, we are talking about a market of 100 billion. This is the market of the quantum products themselves, okay? A sensor or a computer or a communication protocol. We are talking about a typical market size of about $100 billion. Major share goes in computing and then communications and sensing. The economic impact in 4 or 5 different areas, as I told you, the areas like financial services, the automotives, the medical products, and transport and logistics optimization. Particularly, Bangalore will probably be the first beneficiary of a quantum computer because of traffic system. The best way, a far better way of optimizing the traffic flow will be possible through quantum technologies than probably today's best classical computers. So we are talking about, these are areas, and if you take a look at the recent revenue generation by the major quantum computing providers, we are talking about $1 billion of revenue today, this year, with about a 40% increase per year. We come to cutting edge technologies, and I know I am here with a large number of AI experts. I will spend a little time of where quantum and AI come into play. Okay, first of all, there are 4 areas in which we believe quantum will come in a big way, for cutting-edge technologies today. One is AI and machine learning, in which quantum and AI are not mutually exclusive. They are supposed to be complementing each other. I'll show you a little bit in the next slide. In addition to that, we are talking about robotics. Robotics, because today robotics needs to decision-making and precision in navigation, precision in movements. So a more decision-making robots, as well as those robots which will do more specific tasks, will be affected by quantum technologies, driving automation in quantum manufacturing, particularly making secure communications, authentication, and improved navigation and sensing precision will give robots a whole new dimension. Then third is sustainability and climate tech, and the fourth is cryptography and cybersecurity. Cryptography and cybersecurity are obvious. We are talking about hack-proof and secured communication in the first place. All right, as I told you, let's go deeper a little bit on the AI aspect of it, okay? So what am I going to do with AI and quantum combo? Okay, look at the sentence. I deliberately wrote a long sentence. It's a potentially, it can trigger transformative breakthroughs in healthcare to cybersecurity, but we are really treading into dangerous territory. Today, AI is about learning from very large data sets, getting inferences with very large data sets. Quantum gives it the decision-making power, because you are going to span a much larger space using quantum, and that essentially ends up giving the power that what AI-generated information can do with, okay? So we are going to create something which is an autonomous system that are difficult to control or probably understand at this stage. But hey, that's a fantastic area for an academic like me. I would like to see how does AI and quantum superpose. So how quantum and AI can collaborate in both ways. Quantum can help AI in certain ways, and AI can help quantum in some other. For example, if I look at how quantum computing will potentially solve multiple AI training constraints, the algorithm efficiency, the memory size, the memory wall, and the compute power. Extremely important is compute power. Today, looking at the escalation of computing with AI training, AI models, it's going to be impossible in the next 5 to 10 years to actually sustain the energy requirement, if nothing else. It requires 29 gigawatts of power in order to make if you project the AI requirement in US alone, which is about 29 nuclear power plants. That's not going to be a sustainable situation. We have to find alternative ways in which we can offload certain computing load to a new technology which will do things much faster in a far more energy efficient manner. Quantum will have to come in at that point of time. Number one. Even other way, how does AI help quantum technologies? Today, AI will help us in finding good superconductor, better superconductors to make quantum technologies a reality. Well, it is already a reality. It's more efficient in the future. In addition to that, the softwares. For example, if you look at the quantum software and application, AI can support many of the error corrections in quantum technology. So there's a continuous feedback that is going on between quantum and AI as we go along. So this is what I would like to tell a large number of AI enthusiasts here. Right now, we are seeing some sort of a reappropriation of workforce. We are seeing that people with traditional software understanding and knowledge are learning about AI and getting into new job market. In about 5 years' time, it will have to be a quantum AI combo. So if you need to learn about quantum algorithms, you need to learn about quantum structure of a quantum Python programs in order to run quantum gates so that you can take those and hybridize with your AI algorithm. So in about 5 years' time, I'm looking at a whole range of engineers who will come with a quantum AI combination of training. So we need to prepare ourselves for that. What about investment? So this is something which gives you an idea about how quantum and AI are moving in parallel. So if you take a look at the last 4 years or so, this is how the investments in the quantum technologies and Gen AI infrastructure has gone in from 2021, 22, 23, 24. Gen AI has really exponentially taken off, and quantum technologies are more or less where, about $3 billion per year or something of that sort. But if we see the VC deal, plain and simple from the deal size in quantum and AI since last decade, this is a very interesting graph. You see, this is in $1 million. This is how Gen AI or the AI VC deals have taken place, and quantum is now about to take off. So exactly about 10 years back, where AI was today, is quantum is here to now, right now. So this is where we need to now plan, we need to be ready for this quantum revolution that will come into AI and make us a whole different ballgame, a whole new futuristic technology. We have about 5 years' time. We don't have 10. Because of the way the quantum is moving, it is moving faster than what semiconductor industry did about 2 decades or 3 decades ago. So we need to be prepared for this earlier than probably what we are envisaging right now. Okay, so how is the quantum economy developing across the world? And I would like to give you a few examples here. Typically, right now, there are about 20-25 cluster-based approach. What I mean by cluster, the quantum technologies is, after all, infrastructure-intensive technology. You need dilution refrigerator, each of which cost about a few crores. You need whole very different set of manpower, and you need infrastructure to make devices, for example. As a result, there are about 20-25 of them with global impact. Boston, Chicago clusters. This is in Netherlands. Then this is in Oxford. This is in Tel Aviv, China, Seoul. So there's about 20 of them. What do these clusters involve? So there are 5 key enablers in these quantum clusters that are building quantum technologies across the world. For example, we need capital investment. We need funding of research from on the government side as well as from the private side. Physical infrastructure. This is extremely important. As I told you, it is an infrastructure-intensive economy, so we need advanced laboratories and facilities. Then 3 is academic institutions. You see, most of the clusters that are there today is a beautiful and a very symbiotic combination of a cluster of academic institution and industries around it. Okay, so you need continuous feedback because quantum technologies are evolving very, very fast, but it needs continuous feedback into breaking the state of the art. Fourth is industry and government partnerships, and the 5th is accessibility for technology, standardization, and so on and so forth. So these are the 5 key enablers in development of quantum technologies, in a cluster-based quantum technologies. Okay, this is an example, the Chicago Quantum Exchange. Look at what it promises. It's the largest cluster which seems to drive the quantum ecosystem, a state-driven quantum ecosystem in the US. It has economic impact of nearly $80 billion in the next 5 to 10 years. It will have about 191,000 highly skilled jobs, directly quantum technology oriented. It already has about $1 billion of investment from the government, as well as the state and investment of the private enterprises. In addition to that, it has essentially teamed up with industry. This is what I was telling you, that it has teamed up with IBM, it has teamed up with Quantum. So it's an ecosystem that governs the local job market and also aiming towards a large impact on the economic of the local Wisconsin region. So there are challenges, and I have to come to the challenges. And these challenges are extremely important to understand where we are moving to. Because of the strategic nature, and almost every quantum product today are what you call dual-use products. What do we mean by dual-use product? It means they can be used in civilian civilian applications like medical diagnostics, for example. Also, they can be used in defense or strategic applications. So, for example, if you have this is a gradiometer. A gradiometer, or a gravimeter. A gravimeter is essentially those which can measure the vibrations of the earth crust. So if you can put them near the tsunami area, those near the Himalayan, this is on the Mount Etna, where it is supposed to be a dormant volcanic zone. So if you see vibrations, you should be able to predict volcanic eruption. You can predict other kind of natural disasters. So this is good for society, very good. But in addition to that, the magnetometers, for example, like this, which Sandbox AI has come up recently with, is essentially those magnetometers which can measure tiny variations in the Earth's magnetic field. And hence, you can essentially make your aircraft completely invisible to the radar or any kind of communication with the satellites. So these are essentially boxes that you mount on this. Even the Australian company Q Control has come up with these small boxes. All it does is that it measures the fluctuations or variations in the Earth's magnetic field and hence navigates the drone, for example. So tomorrow, if a drone comes in, you will not know. And this is why the strategic applications of quantum is extremely important for national security and safety. We got to make sure that we are ready and sovereign with quantum devices in the country. The problem is that we have got 4 key global problems. First is, of course, human rights. Because it is a very infrastructure-intensive technology, you require heavy, the difference between the haves and have-nots is larger, so we have to find a way to solve that. But in addition to that, collaborations. It is, after all, a scientific collaboration at this stage, even at this early stage of, it is possible that there will be a strong, exclusionary tendencies. People who are working in quantum may be denied visa, for example. So having, even at the fundamental science level, okay? For example, policies. We need to have dialogues. There are IP strategies. IP policies are not clear. If I make a quantum device with another country, for example, it is not clear which country will own the IP, and because it is strategically important for both. And of course, certain technology standardization. As a result, this was about last year, multiple nations, even at this early stage of the technology, is actually doing export control, multiple quantum products. And if you don't believe me, trust me, this was last week's news. EU has just imposed a strict export control on quantum product. The first restricted items is quantum computer and quantum device, and those components which will lead to quantum products. So imagine this happening in 1990s when the computers were starting to develop. We need to be ready with this technology as soon as possible in order to ensure that we are safe and we can be sovereign in this aspect. The key challenge in India, I would like to come to that. In India, the situation is a little different. First of all, private funding. I'll tell you a little bit more on that. Then the problem is, although India produces the largest number in the world, India produces the largest number of quantum-educated people. But still, our output in terms of technology is abysmally small. And the third is, of course, manufacturing supply chain is a problem in India. We are talking about a hardware development. Many people here, of course, AI, we have our computing resources, and often those computing resources can be now bought, and hence it can be made somewhere else in the world. That option doesn't exist for quantum. Okay, and the third, of course, the regulatory aspects, the customer protections and risk mitigations. These are also at a very early stage as far as quantum is concerned. Giving you an example of what we mean by India's problem of private funding. So this is typically how much the federal government in quantum has gone in. It's about $54 billion. The circle size is roughly which a particular country has invested. The federal government of the country has invested in quantum. India has not bad. India has actually, look at this yellow dot. It's about $1 billion, about 1.5 billion, including our national quantum mission. However, if you take a look at the next slide, it will be very interesting. The blue ones are the federal government, which I showed you in the previous slide, and the red one is essentially how much the private funding has gone in that country with respect to the federal government funding, which means that in the case of America, this is $3.8 billion have been given by the government, and the Googles and IBMs and Microsofts, they make about $4.3 billion. So that is why there are more than 100% of the funding to quantum has come from the private sector. If you take a look at Europe, it is less, and you have about 5 to 10%, depending on the country, of the private funding. If you take a look at Asia, China has put in the largest amount of money in quantum, about $15.3 billion, and that essentially is off the chart. And still about in Asia, most of the countries, the private component of the funding is in the order of 5% or so. In India, this is the problem, that we have just about 0.2% of the federal government funding has come from the private funding. So we got to give our private companies, like the Infosys, like the TCS, Tatas, like the Adanis, like the Wipros, that the option of buying computing time and running your business is not going to happen in India. We got to make your own hardware and run your computer, run your services from within the country, because tomorrow you will not get buying time from quantum computing. Okay, so despite large number, the problem of funding, of private funding, has actually caused people not to take quantum technologies as a viable career option. For example, as I told you, India produces 91,000 quantum-educated undergraduates in 2021. It is pretty much the same. It is the highest in the world. But if you take a look at the output from India in terms of patents and publications, it is extremely small. It's right here. Look at the comparison to EU, US, China, etc., etc. So we got to start making our own IPs in this direction. So this is what is happening in otherwise the situation. The government has just come up with the National Quantum Mission, and one of the goals is to create the infrastructure. It's about 6,000 crore investment in various aspects of quantum. In one of the major aspects is skilling the human resource. We just started the undergraduate program in quantum in 9,000 colleges, which is approved by the AICTE, All India Technical Education. We also just started the MTech program in quantum technologies, and in the next few months, a laboratory will be available for extremely large number of colleges to start their own quantum education program. In addition to the national initiatives, now the states are coming up. Different states, originally Amaravati Quantum Valley has just come up from in Amaravati, in Chandrababu Naidu has just started this Quantum Valley project. The idea there is that they're going to buy a 156 qubit quantum processor from IBM and then provide it on the cloud so everybody can actually start computing using the time that is going to be there. Quantum mission in Karnataka was announced. I guess you have seen this in the newspapers of late. Quantum City, which is called a Q City, has now been announced with a state government contribution of about 1,000 crores. So hopefully this will kickstart quantum activities in Karnataka in the next few months or so. I'm going to give you a little bit about what we are expecting from the community, about why we essentially need to have a holistic approach to quantum. Just buying a computer from a company and then giving you the computing time is not going to be the sustainable solution for quantum technologies. For example, how do we bridge the supply chain? So a core quantum product is a quantum circuit. This is there. We have in several places in the country. IISc has it. TIFR in Mumbai has it. So there are some places in this has the core quantum product. We also have now we need to create this quantum associated product, which is like a dilution refrigerator. Yeah, 5 more minutes. And then we require a quantum beyond quantum product, which means, for example, the microelectronics. So this whole thing forms what you call a quantum ecosystem. Okay? And if you take a look at recent companies that are coming up, they are making small products, just a filter in the dilution fridge. Even that is $1 billion business today. And that is why if you see the companies that have come up in the last year or two, they're all in the hardware, in the equipment, small equipments, as well as software and algorithm regime. So what I say that if we have a global market to go to this, we need to have, and in which a real quantum computer comes in next 6 to 7 years. We have about 30 startups right now in quantum domain. But if you are an expert in, for example, a software algorithm, PQC, the post-quantum cryptography, if you are a material expert, semiconductor, nanomaterial, or whatever it is, if you are an expert in microelectronics, for example, or if you are an expert even in heavy industrial manufacturing, we require you. We need all these 6 or 7 different areas must come together into building this ecosystem. And that's essential for quantum technologies to get the sovereignty in quantum technologies. Okay, I'm nearly done here. I'll just give you a sense of what we should prepare ourselves for. Okay, this is the last. You see, quantum, there is something called a Q-day. A Q-day is the definition, is that the point at which the quantum computers will break into our classical encryption and then make all data that we have viable to attack. This is what quantum computers can do. It will actually hack through it once it's in full form. It can actually factorize the Shor's algorithm. It will see the current encryption. It will break the current encryption fairly easily. Typically, today's encryption, the RSA 2048 protocol, which is considered safe to 2030. A quantum computer today will break it in 26.7 hours. So that's called a Q-day, when the encryption is breached by a quantum computer. And the impact of the Q-day is essentially a sensitive data essentially becomes vulnerable. Organization and the governments face immediate need to implement the post-quantum cryptography and quantum key distribution to safeguard this data. And the features will be essentially the breakthroughs in quantum algorithms, and this is happening. So question is, when do you think this will happen? Okay? So if you take a look at the way the infrastructure is growing, so this is typically how the roadmap of industries in terms of the resource, physical qubit is the resource for quantum, right? Typically, this is how we have moved. The amount of qubits that we have in our hand by the industry. This is approximately the dashed line is the reality, what we have achieved in hardware. So it means essentially that what the industries have predicted, our hardware requirement actually has, our hardware development has actually followed that. So it is actually moving with the expectation of the industry. Now, what is the resource required for breaking the RS-2048 protocol under the encryption? That has changed over the years. Essentially, this is the hardware requirement for breaking the RSA-2048 protocol. And as a result, if I have a quantum computer, this is roughly the date from anywhere from 2027 to 2034, 33, 34, there is a chance that our encryptions will be breached and the computers will take the data. Okay, of course, at this point of time, we are working on post-quantum cryptography, making better protocols to safeguard our sensitive data, but this is roughly where things are going to happen. I'm done. This is my last slide. There are certain industries' expectations, but we are trying to keep up. However, I always end with this picture. In 1943, Thomas Watson said that there will be market for 5 computers. Clearly, that was wrong. So the future is something that is rather unknown, and we must be ready for any eventuality. Thank you very much for your attention.